once the webinar start. Yeah.
Okay, I think it's a good time to start the webinar today. Good morning, good afternoon, good evening, wherever you are joining from. Welcome to this special webinar. Today, our presenter for this webinar is Herbert Ulveson. He's going to talk about a very interesting and important topic. Whoever running a network probably find it very relevant and very interesting to listen to this topic. It's about the LibreQoS and measuring the latency. Many of us probably have heard about LibreQoS already. It can really help the internet service providers reduce the customer latencies. Let's hear more about it from our guest presenter, Herbert. Over to you, Herbert.
Thank you. Hi, everyone. I'm Herbert Wolverson with LibreQoS. Today, we're going to be talking a little bit about my journey with LibreQoS and LibreQoS's how inception, how we got involved with the bufferbloat project, how we worked through, and sorry, the Zoom thing flashed at me. How we worked through a whole lot of problems, started to build something that's generally useful for us. And we'll start off by defining what latency and bufferbloat is, work through how we tackled it, work through how we measure it to prove it, and then work through a few ways of looking at over time, and you'll see how it all develops. It's a pretty cool project. I've been really enjoying myself working on this, so I'm really excited to share what we're doing. All right, years ago, I helped start a wireless ISP in mid-Missouri. Our mission was to try and get service out to underserved areas. A lot of areas are really remote. Houses are greatly spread apart. Lots of areas that it's just not financially viable to run fiber to. So wireless it is. And at the time, I had a dream of a pretty much perfect internet in which everybody has all the bandwidth they need all the time. Nobody ever has Wi-Fi issues. They never have a problem at home, at work, or even on the road. And I dreamed that latency would always be stable, predictable, and good. And of those, predictable is frequently the most important because you can work with a stream where you know the pacing of things going through. It's pretty hard when suddenly latency goes terrible or good, terrible, good, alternates between the two. And best of all, in this dream, routers, cables, antennas, signal modulation, congestion, and the physical world always cooperate. Everything goes pretty swimmingly. Unfortunately, then I woke up. And talking to Robert Chacon, who founded LibreQoS, this was his experience too. He had all these dreams. Unfortunately, they didn't always come true. The COVID-19 pandemic was pretty much a disaster for internet service providers. I mean, it was pretty bad for everyone. ISPs were faced with some unique challenges because every assumption that we had turned out to be wrong. Because all of a sudden, all our residential accounts are now business accounts, but they're not paying to be business accounts because they're still at home. And previously, you really only heard from gamers when latency was bad, but now literally everyone is a latency critic. Also, all of a sudden, everybody is at home using the internet all day long, and they're having to learn to coexist together. So instead of having a nice setup that you go to work, have your meetings, suddenly it's, I've got a very important Zoom meeting, so I'm going to do that. But little Johnny decides that it's time to update the latest Call of Duty. So suddenly all your bandwidth is flooded with that download. And at the same time, your 2-year-old daughter decides it's time for a 6-hour long Peppa Pig marathon. And so she's complaining if it buffers. Your Zoom meeting is saying internet is unstable, stuttering. People are saying, what did you say? What did you say? And it's not good. And so the real reason for these problems is that with peak time moving, and suddenly instead of being a nicely defined business peak time and a nicely defined residential peak time, now it's all peak time until late at night when everybody falls asleep. Oversubscription is pretty much the backbone of a lot of ISP financial calculations. Typically, you sell more capacity than you actually have. So if you're selling 10 connections at 1 gigabyte each, or rather 1 gigabit per second each, you're unlikely to actually need to provide exactly 10 gigabits to that area because most residential connections are idle a lot of the time. When they're not idle, they're typically very spiky. So you'll see a big burst and then very little, or streaming video rarely gets above 25 to 30 megabits per second, but you'll see lots of spikes going through with long pauses in between. And it's only really big downloads that start to fill the pipe up. And so you make your calculations based on the assumption that not everybody is going to be doing everything at once. And then a pandemic comes along and suddenly everybody is doing everything all at once continually, and life starts to get a little difficult. And there are plenty of ways to get upgrades rolled out. The problem is that when you've got a highly contagious virus going around, that's not the best conditions to be sending field techs to everybody's house to upgrade their equipment. And so the consensus was pretty much that there had to be a better way. And so Robert Chacon, CEO of LibreQoS, and also runs Jack Rabbit Wireless in Texas, declared, I must fix this. And so he knew all about FQCoddle and Cake, which we'll be talking about in a moment, put together some really nice Python scripts to obtain his customer information, load it all up, set up the scripts, get things going. And he founded the project, open sourced it, made a really solid starting point. And Dave Tutt, our chief science officer, declared that he'd had 14 years of 100 times better internet latency being feasible. Why isn't it deployed yet? He's running the bufferbloat project, and this is very much his ballgame. He hopped on board, successfully nerd sniped me into the project, so you have him to thank for my appearance here today. He's also a great guy to work with and very, very smart and very much laser focused on latency, latency, latency. And so back then I was still just running a wireless ISP, but now I'm chief product officer, mostly because I always wanted to be called C3PO. And I saw LibreQoS, I tested it a bit, and I said, my ISP needs this. And because my other job is teaching Rust and writing books about Rust, I said, I'll rewrite this in Rust. So my ISP was suffering. LibreQoS really did make it work again. And along the way, I started contributing more and more features, adding some Rust to the mix, doing my best to make this into a great project. And it's been great to work with the guys and get as far as we have. And then Frank joined us a little bit later. His message is very much the internet needs this. And he insists on the job title Gopher, but in reality, Frank runs an awesome community, keeps us on track, and helps us connect with other ISPs, organizations such as APNIC, and everybody else who benefits from LibreQoS. Frank is very much essential, and so he's an essential Gopher, not just a Gopher. Okay, so that's the quick introduction as to who we are. We're going to be talking about bufferbloat, queues, and latency. And this is very much underpinning how some of the latency happens and ways that you can go about counteracting it and understanding why it arrives, especially on either lower capacity or wireless networks, but you still find it even on the biggest of fiber. So most routers run what's called a FIFO queue, that is first in, first out. Packets arrive and leave in the order in which they are sent. As you can see from the graphic zooming by, all the packets are going nicely in order, chugging through the queue. All is good. And this is fine so long as you have no congestion, no varying conditions, enough bandwidth, and a reasonably sized buffer. And sometimes that's all true. And if it is, that's wonderful. You don't need me. You can stop watching. But otherwise, quite often, that's not the case. When congestion happens with a traditional FIFO queue, you have more packets coming in than you have going out. And this is quite often because you have more demand at one end than you have at the egress side of the pipe. And that might be a temporary condition, that might be permanent. If it's permanent, then you need a bigger pipe, obviously, but sometimes you can't always have that. But the problem is that they drop when the queue is full, any packets that arrive simply drop, as you see illustrated there. Um, And TCP does make this work, TCP the protocol, because TCP connections use ACKs and resends to find the correct rate at which they should be transmitting data. When there isn't an acknowledgement of data, it gets resent. TCP windows sizes change. Eventually, the TCP connection will find the right rate, but eventually is the key. And when you have a router queue that is consistently full, packets bouncing off the end, it becomes kind of random as to how quickly those TCP connections will start to find the right rate. And now your friend who downstairs decided to update Call of Duty during your important meeting is making your life miserable. And so, reasonable thing to say, we're going to need a bigger queue. And you can, in fact, reduce the pain by building a bigger buffer. And if you're just dealing with transient issues, that does help, because now you have a greater buffer against the queue filling up completely. If you're dealing with longer term congestion, then your buffer is still full. You still have packets bouncing off the end. But now you've got another problem, that the buffer itself is so big that it's become a sort of source of latency in and of itself. Real-time packets are delayed in the sea of giant downloads. If you look at the graphic there, you can see the real-time packets are nestled in amongst a whole lot of other packets. And so as the buffer gets bigger and bigger, you start to have problems that they take longer and longer to traverse the entire buffer. Not a problem if the buffer is mostly empty. If the buffer is full, one packet at a time sneaking out of the end, then you started to run into latency. So the other problem is that when you run out of buffer, you still have the same problem. And so hopefully there's a better way. But worse than that, it's not just your router, it's everybody's routers. Any given packet goes through a lot of routers, especially if you're in a remote area and potentially have to take quite a few hops before you get to a good big internet exchange. And so every single one of these routers has a buffer. Every one of those buffers is potentially going to be full at some point, maybe dropping packets. So it becomes really unpredictable to figure out when packets will be dropping. And TCP's rate finding is quite remarkable, but you won't necessarily you don't have a whole lot of control on it. And with every router along the way implementing drop-on congestion, you've got lots of potential points of contention, fault, latency. So if everybody has an enormous buffer, because big buffers are a common way to solve some of the problem, now you've got lots of sources of potential latency along the way. And that's before you take into account fun things like the speed of light, which gives you a certain amount of natural latency, because it takes a certain amount of time for your data to traverse the internet. Sorry, the Zoom just popped up the QA box over my there it is. Okay. Sorry about that. All right. So Dave and a few other people came along and came up with the original CODL algorithm, short for controlled delay. It's defined in RFC 8289. It's a relatively simple algorithm. It adds sojourn time to each packet. That is, it tracks when a packet enters the queue, tracks how long it takes for data to make its way through the queue. And if it's taking too long, it's dropped from the head of the queue. And so the difference here is that you're actively having packets flow into the queue. And then if they're taking too long, you proactively drop them instead of reactively dropping them because your buffer is full. This has the effect of effectively resizing your queue to be the correct size to match your current latency requirement. And so this also encourages data going through to hit a more sustainable, reasonable speed. So effectively, you're trying to be nice to your routers, get all the packets going at a speed that matches reality. currently, whether that reality is that your internet connection is full, upstream systems are having troubles, or everything could be going swimmingly, and you just need enough buffer to make sure everything flows through great. Cuddle smooths things over. Now, despite being relatively simple to implement, Cuddle unfortunately was not widely adopted. So the next variation they came up with was FQ Cuddle, Fair Q Controlled Delay. And so this is RFC 8290, which keeps Cuddle, so you still got your dynamically sized queues, but it adds what's called fair queuing. So instead of just having one queue, now you have multiple queues that are determined by a hash of the source and destination, and packets get divided between them. And so quite often your download will be coming from one host, your real-time communication, your meeting to another host, your video to a third host. That's not always true, but it works quite often. And so because you then effectively round robin between the queues, so as packets enter, the queues fill up, but each of the queues gets its fair share of time to transmit. Now you're having the nice side effect that you are naturally favoring the sparse queues. So that tends to be real-time communication because VoIP, for example, will be ticking at voice over IP will be ticking at a very consistent rate, but not a lot of data. Zoom video, again, not a huge amount of data, but it tends to be a little bursty, so you have nice sparse queues. Streaming video does great. And so now with Jimmy downloading Call of Duty in the basement, he is experiencing a very slightly slower download because his packets are all being queued in his queue, and a little bit of priority is being given to the person upstairs who's having the meeting, and your daughter continues to enjoy Peppa Pig all day long. So FQ Codal is widely implemented in a lot of OpenWRT routers. There's a few other routers starting to implement it. It's the default on a lot of Linuxes. It really makes a difference and highly recommended. And so Cake, Common Applications Kept Enhanced, is very much Dave's baby. Cake takes everything from FQ Cuddle, fixes a bunch of bugs, and introduces the concept of tins, which differentiate traffic through the diffserv bits and allow it to better prioritize real-time data. So we're still having multiple queues and identifying hashing down to individual hosts. And on top of that, now you're subdividing the traffic, and some of the known marked real-time traffic gets a bit of an extra priority, and you get a significantly smoother experience. Our experience has been that this particularly helps with wireless links. So Cake is great. The only downside is Cake uses a little more CPU than FQ Cuddle, which in turn uses a little more CPU than Cuddle. It's CPU all the way. And so that is how LibreQoS approached solving the latency issue. Cake for everyone. But it's only half of the picture because it's kind of unusual to have a network that is completely flat with everything connected to one router and going out to the world. So we additionally wanted to start modeling the relationship between all the pipes that make up your router, that make up your network. So your internet connection, core router, distribution switch going in our case with wireless network to towers, then sometimes towers to other towers to other towers, and bottlenecks may be moving around. This is true of fiber connections too. It's quite common to hang a pop off a pop for your fiber, and you may have a limited amount of bandwidth relative to potential demand. And so allowing you to realistically model what you have for a network means that the queuing system can start to realize, hey, this pipe is 90% full. I better start applying a little bit of slowdown. I'm sorry, I keep getting distracted by questions. And so once you're starting to model that, and in our case, we use HTTP queues in Linux with Cake, and gives you a nice hierarchy matching the network. And so that brings us to the first problem we ran into. TC, the traffic control in Linux, is quite single-threaded, and we wanted to go really, really fast. And so TC was designed quite a long time ago. And it's really common to set up one of the simple TC scripts and realize that now you have one core in your computer at 100%, and all the other cores are pretty much idle because HTB in particular is really designed for a single core environment. And so that was a problem for us because we wanted to start pushing lots of data instead of the typical 1 to 4 gigs that people were complaining it topped out at. And so Robert found a project online called XDP CPU map. XDP is part of the eBPF system in the Linux kernel. Those are tiny little programs that run for every single packet that passes through on the way out of the driver and into the network stack. And there's a second half that can run on the way out of the network stack and into TC, traffic control. And so we adopted that. It didn't do everything we needed, but it did offer us a way to use queue called MQ at the very top and then hang the HTB trees below it. And all of a sudden, we're using all of our CPUs, gave us a great way to scale IPv4 traffic across multiple CPUs. Problem was, it didn't support IPv6, and they were running headlong into this about the time that I signed up. So that was the first thing I did was I broke out dusted off my C skills. I added IPv6 support, committed it back upstream. So they have it, we have it. We also needed to support CIDR, for example, 192.168.1.0/24 as one entry instead of having to store all 254 items in a hash map. That turned out to be relatively straightforward and a natural extension of what you're doing for IPv6 because there's no way you want to add millions of IP addresses to cover all of the possible addresses somebody might have with IPv6 at home. So we added that. The Linux bridge was giving us some troubles because sometimes we'd see huge numbers of interrupts. So we implemented a bridge with XDP. And now we could have our cake and eat it. Fast quality of experience on all CPU cores. And all of a sudden, we were testing at 25 gigabits per second instead of 4 gigabit with 16 cores, each around 50% utilization, which some of the customers we've worked with tell us that that's enough for 10,000 subscribers per shaping box, obviously, depending on how much bandwidth you're giving your subscribers. And we still don't think that 25 gigs is enough. So we're working on 100 gigs on affordable hardware. The network card, the Mellanox we're testing with, is definitely the most expensive part. We've reached about 70 gigs on 16 cores so far on about a $1,500 box. So we're definitely making progress on this front. So in 2021, LibreQoS is born. And at this point, we can use Cake to fight bufferbloat and improve latency. We can use HTB to model your network. We've got XDP CPU map to scale to large networks, 25 gigs or more. Adding it was deliberately pretty straightforward. It's effectively a bump in the wire, a transparent bridge that you insert with one connection facing your internet router, one connection facing your interior router. It reads inside VLANs, reads inside PPP and similar setups. And it's just a transparent bridge that applies the traffic shaping on the way through, and it integrates with various CRM solutions so that it can find out how fast your customers should be going and apply the appropriate speed limits. And so with that going, we said, that's great, but are we helping? And anecdotally, customers stopped calling our tech support. Both Robert and I saw this, and we stopped getting the infamous call that our internet was slow or online meetings were failing. One of our customers says, working beautifully, fully integrated with our Splinks, which is a CRM, customers stopped calling. And that's the message we hear over and over again. But anecdote isn't evidence. I wouldn't expect you to believe me giving this quote. So let's start digging through how we started trying to measure the problem and measure the improvement. So a large part of LibreQoS and a large amount of the time was spent measuring the user experience because really, without hard metrics, you can't know if you're helping. We started off using Polera Peeping, which is an open source tool that sniffs traffic, also transparently, matches the timestamps on TCP packets going each way, which allows it to deduce a round trip time for TCP connections. It's a command line tool with a web interface. Really nice tool, gives us what we needed, but we had terrible troubles when we started scaling up to 20 or more gigs, that it was eating more CPU than the actual traffic shaping. And that's not good. You don't want your passive shaper to be slowing everything down, and you don't want your passive monitoring to be slowing your shaping down. So we started looking for more alternatives. Now, the XDP project, once again, saved the day, working on a project called XDP pping, which acknowledges the original Polaire pping. Once again, it's in eBPF. So raw packet data straight out of the network stack gets analyzed, data sent to userland for analysis, really fast, really accurate. So we started integrating it into LibreQoS and offering them any of the changes and improvements that we made. It's very much formed the backbone of 1.4's version, LibreQoS version 1.4's analysis capabilities. But we still wanted more, so we've been busy expanding its capabilities, implementing more and more, and doing everything we can to go faster. And so we wanted to integrate our existing eBPF stack, that is all the XDP and TC code that we already had. We really wanted to be monitoring TCP round trip times, pping does that, TCP retransmissions, because that's often a good sign of where the problems are, individual host throughput, so not only are we pushing 400 megs, we want to know exactly which of our customers is pulling what, how much data. Start dividing the network up into flows, which we can track by ASN, autonomous system number, geographic location, because you can get geographic information for most IPs, round trip time, obviously. We wanted to provide packet capture to ISP operators, because if something's not working, a packet capture is frequently the best tool to figure out what's going wrong. And we also really wanted to provide analysis to help the science behind the bufferbloat team and give Dave stuff to do, and hopefully lead to more discoveries that improve this even further. And so we're a little crazy. We're trying to monitor 100 gigs at once. So we're going to walk through some of what LibreQoS can do for you for telling you what's going on. This is the most basic screen. Real time, how much traffic is going through. The test box I was using had about 300 to 400 megs going through. We're also a count of flows with 300 to 400 megs, and on a small ISP, it's not uncommon to be tracking 13 to 14,000 flows at a time. A flow being either a TCP connection, or if you have UDP lined up with the source and destination going back and forth, and you can see it's a flow. ICMP pings are a natural one because you have ping, ACK, ping, ACK. That's how we track flows. Since we're tracking the TCP round trip time of every single connection, now we can start finding interesting ways to plot them. The histogram is my personal favorite, where you simply count how many of the current flows fall into each latency bucket. And so this, when I recorded this on one portion of my network, you can see over to the left, the vast majority of the network has really good latency, 50 milliseconds or less on round trip time, which is kind of what you see in this day and age of CDNs, where everything is somewhat local. And then you've got a few outliers and a few things over at the far right that are red, not doing well. Those are things that we may want to investigate. You'll always have a few because of slow running or mostly idle connections, but generally, this graph is a great way to start. And when you first plug this in, everything is orange to red. Once you start applying cake and using the tools that we give you to help you find the problems on your network and start improving it, it becomes kind of a game to move this as far to the left as you can. All right, warning, there are Klingons ahead. Because my customers probably don't want me giving you all of their names and addresses, we put in a privacy feature in LibreQoS that can replace all of the English with Klingon. And simply doing a letter by letter translation wasn't going to help because you can just change the fonts and see them all back. So we also hash them, put them into a dictionary, and translate them into things like "your mother has a smooth head," which is a joke from Star Trek. We're all a bunch of nerds. Hopefully you find that funny too. Okay, so real-time top 10 circuit flow gives you a display on the dashboard at all times of who the top 10 users are by bandwidth. The flows screen is the same thing, but for the individual flows. So now we can see that we've got some HTTPS and QUIC really dominating things right now. Not a particularly fast connection. We've got round trip times, upload and download. Geo endpoints, we're tracking the location of each of these flows. And this starts to get interesting because now we've got round trip times by parts of the world. Protocols is mostly because we're interested in what's going on the network. It's great to see that Quick is taking off. Ether types, this is kind of an embarrassing one for me because my upstream does not support IPv6. If it did, there would be some interesting numbers there. But this is a great way to log in, get a quick tactical view of what's going on your network, how things are going. Let's see, I just saw somebody ask, what can I say a little more about what pping does? Pping is a packet sniffer. It catches packets as they go through. Each batch of data in TCP has a timestamp attached to it, and then the acknowledgement saying, hey, I received that, will also have a timestamp. So you can watch for the timestamps in each direction and then time between them to understand the round trip time that the packet took. That's what pping does. UDP and gamer experience. UDP is more difficult because UDP doesn't have built-in backoff. But UDP protocols are frequently designed on the assumption that things will start dropping your packets. Gamer experience, our gamers have largely stopped calling us, but I don't think there's anything we can do to make them always stop calling us. Going back, real-time worst 10 is the same thing, but we track the worst RTT round trip time and the worst number of TCP rate retransmits, because this is a good example. Somebody up here with 90 retransmits in the last few minutes, that probably means that we need to go out there and look at their Wi-Fi router. And then because we're modeling the whole network as a tree, we can navigate the tree, see exactly how much bandwidth is being used in different parts of the network, what their round trip times are like, can zoom in all the way down to an individual client. When you get into an individual client, you can look at the cake stats in near real time. So this customer has a lot of best effort traffic up in the top right. They have a bit of video traffic, and in this case, video is interactive video, so they're probably having a Zoom meeting like this one. And there's a fair amount of voice packets going on. So this is a great example of Cake helping because their overall experience is great. They're downloading 40 megs on a 50 meg connection of some kind of best effort traffic. That's probably a big download. They're also having a web meeting. Their web meeting is still working. This is Cake in action and functioning. We also, since we've got all the flow data, for any customer, you can look at what they're doing right now, see exactly what's going on. And see, this will often allow you to see round trip time to individual ASNs. Maybe one is particularly suffering. That's a sign that you have some work to do with your backhaul. Or need to talk to your upstream, find out what's going on with their connection into Oregon, for example. And lastly, at any time you can perform a capture, grab a bunch of packets. We have visualization tools that allow you to recreate the famous mice and elephants paper from 2002. Various ways to drill down, look at individual packets, or you can just export it in PCAP, for example, to take it into Wireshark and use that to analyze in greater detail. Then we started having way too much fun. I started rendering all of the flows my ISP was currently using, but it looked way too much like I was playing video games, so we didn't keep that display. Instead, we went to a more useful map that you can zoom. The circles become larger as there's more traffic going into them, change color from green through red as the latency is worse or better. As you can see, we're actually pretty well connected at my ISP, but there's a few spots there, like Venezuela, we apparently have terrible latency too. This is quite useful for determining where your upstream connectivity could use some work. And so before version 1.4, we had all the features I mentioned before. Use cake, HTTP, CPU map, bridge, and receive fewer support calls. But now with a technical view, we can see hotspots and pain points in real time, drill down and start finding what's going wrong with the network right now. We find it particularly useful. We receive a call, zoom into that customer's circuit, have a look at what's going on right now, capture some data if we need to. And also, we're really excited to be working with the bufferbloat people to give them the data they need to try and make things better. Lastly, because people keep asking, those are the install steps for LibreQoS. Then you answer a few questions on a setup screen. Most of our users are up and running in about 5 minutes. Okay, before I dive into LTS, I see there's quite a few questions appeared. How much traffic could go through LibreQoS and processing the queue? We have peaked at about 70 gigabits per second right now on a $1,600 Ryzen box with a 100 gig network card. BBR is a great way to so this is more WAN accelerator territory. Currently, we're not rewriting TCP windows at all. We are just focusing on packet pacing. That is making sure that we're playing nice with reality and having packets flow through at what we consider to be a reasonable speed. When interfacing, it is a good idea to shape your egress traffic to match the ingress police burst on other networks. And that is awkward. LibreQoS will improve the mismatch. It won't fix it completely. How do we shape encrypted application flows? We're not actually reading inside the packets beyond the header. And so we don't really care whether your data is video, voice, a game, or anything else. We're net neutral. We're not distinguishing between services. Okay, so long-term statistics is the second half of this setup. Having a technical view is great. Sometimes it's a good idea to also have a long-term view to give you an idea of what has been happening in the past and draw some trend lines to the future and try and avoid the need to suddenly dash out and upgrade something. If you can see that it's coming, you can have more time, you can do it right. And so long-term stats gather this data, presents it as actionable information over time. LTS is also not free. It's hosted in the cloud. And part of this is to help fund the LibreQoS project, because generally we're all volunteers doing this because we love it. But it's really nice to eat. So LTS covers our running costs and a little bit more, gives us some play money. And so if you can afford it, we would very much like you to use it, obviously. And so it is pretty much a time machine for your data. We log almost all of the data that your technical boxes are holding, make them available over multiple time periods, potentially years or more, but we haven't been running it for that long yet. You can have views of throughput in bytes, throughput in packets, child sites. So since we're identifying where packets came from on your network, you can start to navigate down the tree and see which parts of your tree have data over time, where they're coming from. It's a great way to understand your network's utilization over time as opposed to in real time and having to stay up and make sure you're in the office or somewhere you can get to the Shaper box to see what's really going on at peak time. We love heat maps. The top heat map there is showing round trip time below one of our sites over the past 48 hours. The one at the bottom is showing utilization. And you'll notice that some of our links are quite overutilized. In fact, we have really high oversubscription rate on this setup. And despite that, Cake is doing its job, ATB is doing its job, latencies remain pretty manageable. Usually when you start, you'll see this as a bit of a sea of red. That's great because that inspires you to start making the changes that improve things. LibreQoS helps a lot. also helps a lot with finding the items that are underperforming so that you can either rip and replace, fix them, or make changes as needed. It's as much of an art as a science in some ways, but having the numbers to back up that, yes, this is the problem, makes it a lot easier, and it makes it a lot easier to go to your bosses and say, this is where we need to start putting some upgrades in. And we took the dashboards pretty seriously. We have one site there, all red. I don't know if you can see my mouse cursor or not. They are actually oversubscribed by about 2000%. They are selling way more bandwidth that we've oversold that site way more than we probably should, and because of LibreQoS, we're getting away with it. So the first thing I do most days is I pull up the heat maps, I have a look, and tells me what's going on. And yes, there is a monitor mode, Ryan. You can either use a port mirror or you could put it inline and just not apply the shaping. Supports both. We've monitored live close to 90 gigs a second currently without actually applying any of the queues. And so that's quite a useful thing to do. I would encourage you, if you are doing that, to also consider that maybe you need some of the queuing. From a wireless network point of view, which is what I'm doing, it's kind of nice to have reports telling you things like which access points are getting full at peak time. That's what this is doing. You can see that we have one there that spends 97% of its time between 90 and 99% utilization. That's a terrible thing, and that's an access point that desperately needs to be replaced. But reality is struck for various reasons. It hasn't happened yet. It will. And you'll see the configured capacity is really low. That's because it's an old access point that is a really long way out and really hard to get to. And there is much more. We're always expanding the capabilities. We are ISPs, but we're also hobbyists. This is an open source project. And so we are adding features pretty much as fast as we can in between all our other day jobs. And also as people come to us and say, hey, this is a good idea. Always good to hear good ideas and figure out that, yes, we can do this, or some of them, no, we can't do that, but that happens. And we're increasingly helping other industries as well. So we've got everything from mining systems to academe looking at this, as well as internet service providers and data centers and multiple dwelling units, apartments. It's quite a flexible system, scales down pretty well, scales up pretty well. It's well worth a look if you have a network that potentially has congestion issues. Now, if you're a home user, you probably want to go with something like OpenWRT because having a hulking Ubuntu server is kind of overkill for your home connection. Okay, there were a few more questions. There is a monitor mode. We did that. We do support Ubuntu server as our primary preferred. I know there's at least one person using Debian. Running it in Docker is not going to work because Docker doesn't have full eBPF access to packets passing through a bridge, as far as I know. If it does, that's changed because last time we tried, there was no way to, we couldn't find a way to make that work. There are multiple queues, voice, video, best effort, and the identification is based on the header. It relies on DSCP. Are there plans to implement queue management on hardware? I would recommend talking to Dave Type about that. He's actually in the chat here today. He has been screaming from the rooftops at manufacturers to start implementing some of this in hardware for more than a decade. So we wish there was good hardware support. Does it support Cake with auto rotate? Not currently is the answer because this is currently focused on an ISP. And if your backhaul is changing with the, as rapidly as a 5G connection, which is what auto rotate was originally built for, you've got bigger problems than that. And I haven't worked on auto rate itself, so I'm not the best person to answer for that, that one. Okay, so LibreQoS adoption. Since we got started, we've now had deployments in 44 countries and 22 US states. We are all over the place. We have been particularly successful out in remote areas, areas that need the most help, but we've also got adoption at fiber networks and so big and small, all over the world. And it is frankly amazing to hear from everybody telling us about their installs, telling us how it's working. And we love to hear from you guys. So LibreQoS is offering consistently low latency and statistics to ISPs all over the world. And this is something that was sent to us by a customer. They used waveforms bufferbloat test connections periodically, keep sending us these, and they consistently go from about a B or a C before they put it through LibreQoS to about an A+, and sometimes an A. And that's what we like to hear. Very little extra latency under load, and that's all because of the pacing and the queues. So you're being nice to the network. And so as I was joking earlier, we are being nice at scale. And that's really what Cake's about, is be nice to your hardware, be nice to the network. And just want to call out and say thank you to Equinix and NLNet and several donors. They've made all this possible. And the inevitable call to action. We would love to help you if you're an internet service provider. If you pop by LibreQoS.io, there's lots and lots of different ways to get in touch with us. The core software is all free software, GPL version 2. So it's open source. It's there for you to use. It's free. We'd like to help with any network projects that you have. Obviously, there's only a few of us and only so much time, but we love to help. This is all possible because we get grant money from NLNet, and Equinix are donating the use of a whole lot of test hardware, because otherwise we really couldn't afford to be playing with quite so much hardware and quite so many toys. And we would very much like to spread internet equity, help the underserved get the most out of their internet. And if you believe in that mission, we would love to hear from you. If you want to hear more from me, my new book, Advanced Hands-on Rust, is now in beta with the Pragmatic Programmers. And I'll be at RustConf in Montreal teaching a workshop, but I'll be there for the rest of the conference. And I would love to connect with anybody who wants to talk about this or pretty much anything else. Lastly, one more thing, LibreQoS 1.5 beta is coming out really soon. We managed to, with some new features in the 6.x Linux kernel tree, lower CPU usage by about 30%, which has greatly improved throughput. All of the per flow tracking that you saw here is being implemented. On a technical level, we've moved from having giant memory maps in the kernel and iterating them from user space to a channel system where we're sending events from the kernel into user land. Kind of complex programming, but it greatly improved performance. We're looking at a better user interface, and if anybody wants to help with that, that would be fantastic, because right now, none of us are really UI guys. We're all networking guys, so we're doing the best we can. And all of this is powered by you. Contributions of code, money, anything else. This is an open source project. It's as much your project as it is ours. And so we love contributions of any type, even if it's just, I wish it did this, or here's some code, or anything along those lines. All right, let's go back to the QA, because I see there's quite a few questions been stacking up. I tried to answer a few of them as we were going through. I'm getting a little confused because I have a chat and a QA. And I have pretty much missed the chat, so yeah.
Yeah, how about I'm gonna take a look at the chat window and we'll pick any questions if there are any. But yeah, please go ahead with the Q&A section. I'm gonna check the chat window. Thank you.
Okay, so for level 2 queuing, for level 2 network, how can queuing be implemented? Well, you lose the ability to have a hierarchy. You can define a flat network instead. Plenty of our customers do this. It actually gives you the easiest distribution across CPUs, but you can still, because it's a transparent bridge, there's no routing involved in LibreQoS. It literally just passes right through. We can feed the traffic through Cake. There won't be much HTTP going on, but you still get significant benefits. I know of at least 2 fiber networks that work this way. One of them's in Poland. And I know there's a ISP in New Zealand who do this, so I know it works. It works pretty well in our testing. You really don't need to, if you don't have a natural hierarchy, you don't need to force one on yourself. So level 2 networking is pretty easy. When I say access points, in this case, we're a broadly diverse wireless ISP. We have everything from some old WiMAX system to Cambium Medusa to a whole bunch of Ubiquity stuff, which is basically 802.11 AC, but with Ubiquity's timing changes. We're starting to use a little bit of 802.11 AX. And I know some of our users have their own LTE and 5G setups. It works with that. Works with fiber too. When I was talking about access points, I'm frequently referring to the router at the actual home. Like when you see a whole lot of TCP retransmits over and over again, 9 times out of 10, the culprit is the Wi-Fi router in the house and not something on your network. Oh, I actually already answered Cake with order rate. We don't directly support order rate. So usually BNG PPPoE server installs queues, policy maps. Does the queue of BNG invalidate the function of LibreQoS? No, it doesn't. Most of the time, the PPPoE setup is a pretty primitive policing system that's enforcing maximum speed. Cake is very much a pacing system, which is a different idea. You're trying to slow the packets down to find the natural rate. And so as long as LibreQoS knows what the maximum should be, so it doesn't start trying to feed more data through than makes sense, the policing just won't be doing a whole lot, but LibreQoS will continue to take into account the effective rates and flow of each of the individual queues, each of the individual queues that you're tracking, flows that you're tracking, and pace things out. So I hope that covered that. But we've got plenty of examples of people working with that routine, and LibreQoS can actually read inside PPPoE packets in passing. You don't need to de-encapsulate them just to read them. Is there any presentation that delves deep into the implementation details of LibreQoS? Not really. I would love to give one sometime, but it might have to be a day long. If you head over to our GitHub, all of the source code is there. If you head over to our ZLib, I would love to talk to you about it. In fact, I can talk for way too long on this topic, and I'm keeping an eye on the time so I don't. Unfortunately, we don't have any one presentation or document that contains all of it right now. Also go to bufferbloat.net, and there's lots and lots and lots of information there about CODL, FQCODL, and Cake. Can you please describe the differences between LibreQoS and other QoE solutions out there? Okay, so first of all, we're free and open source. That's a pretty big differentiator. Persim is in the wireless industry, at least the big guy. They actually use FQCODL. They don't use Cake. They offer a very limited 2-tier hierarchy of either shaping just the circuit or shaping what they call an access point, which could be any sort of POP, and the customer is connected to it. They really focus on graphs and metrics. Parakum and Bequant are both pretty heavyweight DPDK, so direct packet plane QoE solutions. They're both really good. Neither of them are all that cheap. Or Parakum does have a low end, does have a free for a certain number of subscribers now. They both require more hardware than we do. Neither of them are open source, and I really haven't had a chance to play with some of the really big systems out there for like Sandvine, so I don't really want to try and speculate too much on Sandvine other than somebody told me if I had to ask, I probably couldn't afford it, and we're a small ISP, so we preferred to go with the inexpensive or free options. There are talks about NetFlow ingestion. That one kind of surprised me because right now we can emit NetFlow data to be ingested elsewhere. I actually don't think we can ingest NetFlow data at this time. So I'm not quite sure where that came from. I think Dave may have misspoken at some point. It would be relatively easy to implement at some point for long-term stats, but that's not on the current roadmap. Right now, we can emit NetFlow 5 or 9 or IPFix packets for collection elsewhere, track all of your flows, but we don't currently have a way to read that data as it comes in. Is there any open source network monitoring tool which can detect network latency issues? Obviously, LibreQoS. It's pretty common to see smoke ping hooked up to a graphing system. It can do various ping type methods and start telling you where the latency is across your network. In terms of global monitoring, though, monitoring everything going in and out, you pretty much need a passive solution like LibreQoS, pping, the XDP pping that we mentioned earlier, hook it up to some sort of graphing solution, and spot it that way. This was pretty greenfield territory when we started getting into it. We didn't find there was a whole lot out there that was already doing this, which is part of what made it so exciting to jump into making this work. How can ISP use LibreQoS as most devices are Cisco Juniper boxes? You add a Linux box in between your routers because unless Cisco or Juniper want to hand us a giant wad of cash and help us get it on their hardware, right now that's the best we can come up with. Want more bandwidth in the network mostly fix things, i.e. why bother with this? Well, more bandwidth will always help. It won't necessarily take care of all of your latency issues, but yes, adding bandwidth does solve the problem to a certain extent. You also have to take into account that not everybody has that option. So if you're out in really remote areas, maybe Starlink is your only option. And guess what Starlink did? They applied FQCODL. They greatly improved their latency. Despite being 150 megs connections, they had latency problems. We've worked with fiber companies who, by applying some FQCODL at the endpoints, started to see substantially improved overall latency, particularly during peak times, because not everything always works all the time. If you are running a huge network, you may not need LibreQoS. You may want to try the monitoring to have a look and see if you do. Does it require two interfaces on a single card? You can use separate NICs, or you can use what we call on a stick mode with an ingress VLAN and an egress VLAN. Can we integrate with Radius Desk? I don't know. Hit me up on Zulip and we can talk about it. We'd need a way to get your user plans and currently assigned IP addresses out of Radius Desk and into LibreQoS. Dave Seddon, I think it's answering somebody else's previous question. SS minus TCP minus info does the job. Virtualization isn't the best idea. I'm actually running it in Proxmox on a 4 gig connection and it works fine. You just have to make sure that you have enough bandwidth. The main reason we say please don't is that if you use something like VirtualBox that doesn't support multiple queues on its interface implementation, it doesn't work at all. And you have to really know what you're doing to make sure that, for example, you pass the hardware through in the NIC through directly in Proxmox. Going through the virtualized layers really hurts performance. So we're not saying don't do it. We're just saying it's not necessarily the best approach. Is LTS the only method to source stats? We do also currently support InfluxDB, and it's open source, so you're welcome to come and add some more. But LTS is, of course, our preferred mechanism because that is what we like to use, and we're pretty focused on improving it. You probably could install LibreQoS on CentOS, but we wouldn't support it because we need to with such a small team, we need to keep the number of distros we support down or we're going to go crazy. What's the difference between LibreQoS and L4S, which I didn't think was an Apple thing. And honestly, I don't know enough about L4S to really comment other than I keep hearing negative things. And if you may want to get in touch with Dave Tutt to hear about that and make sure you ask him very loudly because he will probably give you a very long answer. He has actually been working on a Cake Maint project to integrate some L4S support into Cake. I just don't know the details of that. From what I've heard, L4S is not necessarily the best answer. I just don't really know the right answer to your question. I'm sorry. All right, I am, according to my clock, right on the hour point. So I just wanted to say thank you, APNIC, for having me. And I've greatly enjoyed this. I hope you guys have too.
Thank you, Herbert. It was really an interesting session, and I can see from the chat box and also from the number of questions that we received that our participants well enjoyed this session, and it was very informative. And I hope this session is very useful for them so they can actually try LibreQoS in their networks. For the participants, the recording of this session will be available on our Academy portal, academy.apnic.net, after a couple of weeks. So please keep an eye if you are interested to see the recording. Also, please feel free to participate in our survey that we posted on the chat window. This helps us understand our improvement options there. Once again, thank you so much, Harvard, for this very nice presentation. Thanks, Dave, Frank, and the team from LibreQoS who helped us answer the questions, respond to the chat window. And also, thanks to our audience for joining in. And we look forward to seeing you in our future webinars. Thank you, everyone. Have a good day.
Thank you.